Okay. Last time we did something really cool, the fundamental theorem of line integrals. And so what does it say? It says if you have a piecewise smooth curve, ooh, what happened there? Don't know. Piecewise smooth curve on an open region, and you've got a curve described by a vector valued function, then if you can prove that your vector field is conservative and you're trying to do a line integral like this, you don't have to really do all the hard work for the line integral at all. You don't have to, and even if they didn't parameterize the curve, you don't even have to parameterize it. You just go get the potential function and evaluate the potential function between the ending point and the starting point. So that's a really nice thing to have. After we did the fundamental theorem of line integrals, we also did another theorem that had to do with independence of path in conservative vector fields. And it basically said, it was an if and only if statement. If you have a line integral that's independent of path, if and only if your vector field's conservative. And you can read it backwards. If the vector field is conservative, your line integral is independent of path. They are both simultaneously true every time. So that's kind of good to know. We did a couple examples with that. So what's left? Well, there's a little bit of wrap up. I got to tie up some loose ends for you. First of all, I haven't taught you how to show that a three-dimensional vector field is conservative or not. You got the 2D version, but not the 3D. So here we go. I'm going to finally give you. So if you have M, N, and P have continuous first derivatives on your open region R, and those are the components of your vector field, your vector field is conservative if and only if all three of these things are true. Now, one of these things you've seen already. You've seen this one already. When? Anybody know? dn dx equals dm dy.
That was during the 2D, wasn't it?
Yeah, this is to show a 2D vector field is conservative. You just have to show that dn dx is equal to dm dy, and that's it. And then your two-dimensional vector field is conservative. But for a 3D, you've got to do that one and two more, and they all have to be true. If even one of them is not true, that vector field is not conservative. Okay. Some definitions here. If you see m dx plus n dy plus p dz, that's known as differential form. And we went over this for line integrals already, because if you've got a line integral, m dx plus n dy plus p dz, that line integral is in differential form. And of course, you could do for a 2D also. A 2D would just look like m dx plus n dy. That's a differential form line integral for a two-dimensional vector field. Fine. But what does it mean when your differential form is exact? This is very important. Unfortunately, not so important in the textbook we're using because it's kind of weak when it comes to Calculus 3, but I think it's important, so you have it here in my course reader. So how do you know when your differential form is exact? When dp dy equals dn dz and dm dz is equal to dp dx and dn, can't do that, dn dx is equal to dm dy. All three of those have to be true. In other words, it's when your vector field is conservative. So that's when you have something called an exact differential form. Okay, so what? Well, it's really helpful to know that, because when I give you some test questions, the way I'm going to word it is I'm going to say something like, show that the differential form here is exact. Yeah. Okay. So know how to do it. We'll do this example first, though, example 5. So here is a vector field, and we're going to prove that this line integral is independent of path. How? Well, if on that previous theorem, we just have to show that the vector field is conservative, and we'll show that the line integral is independent of path. Fine. Then what? We'll actually evaluate the line integral where the starting point is 0, -1, 0, and the ending point is pi halves 1, 1. Fine. Will we have to parameterize anything? No. We're just going to use the fundamental theorem of line integrals. Now, we do have to go get mama. We got to go get that potential function, and that's going to involve a little bit of work. But once we do, I think it's less work than parameterizing. Okay. So let's show that it's independent path. How? So what do we need to show? Show F is a conservative vector field. How? Well, you got to show dn dx equals dm dy. Does it? Let's do that one first. So m, n, and p in that order. So dn dx. Dn dx. Well, I got to take the partial with respect to x. So 2y sine x has the partial, I think it's 2y cosine x. Plus, and then e to the 2z, when you take the derivative with respect to x, what do you get?
0.
So we're done with dn dx. Let's get dm dy. So the derivative of y squared cos x with respect to y is 2y cos x. Hey, these are equal. Check. We're good to go. But we have two more things we got to prove. So how about if we show dp dx is the same as dm dz? Okay. So dp dx, well, p is 2y e to the 2z power. And if you take the derivative of that with respect to x, there are no x's in there. So it looks like a constant. So I get 0. How about dm dz? Similar situation because m is y squared cosine x. There's no z's. So when you take the derivative with respect to z, you get 0. Check. Those are equal. We're getting pretty good. Now what? We got to show one more equality. dp dy is the same as dn dz. All right, here we go. dp dy. Well, the derivative of 2y e to the 2z power with respect to y is 2e to the 2z. Does that equal dn dz? I don't know. Let's figure it out. And, well, the first term, 2y sine x, when you take the derivative of that with respect to z, I get 0. But what about the derivative of e to the 2z with respect to z? I get 2e to the 2z. Check. These are equal. Fantastic. So what do we shown? We shown that the line integral is independent of path because the vector field is conservative. So we showed it. It is indeed, that says indeed, independent of path. That line integral is indeed independent of path. So now what? Well, if we're going to evaluate this line integral between those starting and stopping points they gave us, we're going to need to go get the potential function. So that's what's up next. And of course, I never give myself enough room. So let's recover the scalar function, which is the potential function fxy. fxyz, I should say. So how do we do that? We're going to integrate m with respect to x, then we're going to integrate n with respect to y, and then p with respect to z, and then we're going to add up the results, except if there are any duplicates, we will only take one instance of anything that looks like it does get duplicated. So the m was y squared cosine x. So let's integrate y squared cosine x with respect to x. I get y squared sine of x. Now, if you fail to put plus another function, and watch out, since we are recovering the potential function with respect to x, we had to hold y and z constant. So we weren't integrating with respect to y and z. So this extra stuff that we're going to add on there could be a constant, but we're going to call it g, and it's a function of y and z. If you fail to put this on your exam papers, -1 point. And then n dy, so we're going to integrate 2y sine x plus e to the 2z power with respect to y. So the 2y sine x with respect to y is y squared sine x. The antiderivative of e to the 2z with respect to y is y, e to the 2z, plus extra junk. So choose a different letter now, something other than G. I don't know, how about H? h of x and z. So we're acknowledging that we didn't integrate with respect to x and z for this particular result. And we're acknowledging that there could be, you know, more stuff with those variables. All right, so now we're going to integrate p, which is 2y e to the 2z with respect to z. I get y e to the 2z plus extra junk. Choose a different letter, f, and f is going to be a function of the two other variables we didn't integrate with respect to. Please know that for each of these, if you don't remember to write that, -1, -1, -1. Yeah, you have to put that on there in my classes, okay? Because I'm giving you this sweet trick on how to recover potential functions, you have to play by the rules of recovering this potential function using this cool trick, okay? Now, question?
Yeah. Since we were integrating from respects to 2z on the p function, when oh, never mind. I see. I didn't see the 2y.
Okay.
I was a little confused there.
Okay, so what are we saying? The potential function, which is a function of all three variables, is going to be what? Now you got to be careful because I'm noticing that y squared sine x is showing up in two locations. Should I add them together?
No.
No, do not do that. You'll just take one instance of it. Plus anything else? I got duplicates of those guys. Should I add those two together? No. Take one instance of that. And that's pretty much it. And then you can put plus c, because now you can say there's just some pure constant. And now what are we saying? What we're saying is that this line integral, which they asked us to evaluate, is simply going to be this function here, y squared sine x plus y e to the 2z. And you can delete the plus c because it's going to subtract out. And you'll evaluate this potential function between the limits. Yay. And so we'll do that. Always plug in the finishing point first. Don't do this backwards, folks. You'll be sad because you'll get the wrong answer. So I'm just substituting everything here and then minus, and then I'm going to substitute that lower limit, which is the beginning point. So I'll have, let's see, -1 squared sine of x, which is 0. I don't know what I was doing here. That's weird. Plus, and then I have y, which is -1 e to the 0. Okay. To the 0. Now this right here is 0, but this is not 0. So be careful because e to the 0 is not 0. So sine of pi halves is a nice number because that's 1. So we have 1 plus, and this looks like e squared minus a -1. But that's really a 1. So our final answer is 2 plus e squared. And there we have it. That is the line integral result right there. Any questions so far? Fundamental theorem of line integrals. You gotta love it. And now you saw the fundamental theorem of line integrals with a 3D vector field. So to recap, if you are going to use the fundamental theorem in my class, every time you are going to plan to use it, you first have to show me that the vector field is conservative. I won't be too happy if I see, you know, people just going, oh yeah, I know I can use it because I just know. Okay, that's good to know, but prove it. Okay, so example 6, we're going to show this differential form is exact, and that's just equivalent to showing the vector field's conservative. And then we'll use the fundamental theorem of line integrals. And so what are we going to do? We're going to evaluate when the curve goes from this point to then to this point. And then, so this is like C1, the first part of the journey. And then we're starting where we left off, and then we end up here, C2. So do we need to do two separate line integrals? Because it looks like the overall curve is the union of these two separate curves. What do you guys think? Should I evaluate this once for C1 and then once for C2? I've done that before where we had a curve that was piecewise smooth.
You shouldn't have to if it's conservative, right?
That's correct. And here's why. Have you ever been going on vacation somewhere and you had, a plane trip, but it had a layover somewhere? It was one of those type of trips that was not nonstop. So you went, like, say, from San Diego to Chicago and then Chicago to New York. Do you even care about Chicago? You do not, because you don't even get a chance to, usually get off the plane, or if you do, it's like just to go grab a different plane. You only care about the beginning and ending points of your journey. Similar when you are evaluating a line integral and the vector field's conservative. You don't even care about any intermediate stops. Heck, I don't even care if there were 5 intermediate stops. You only care about the beginning and ending parts of your journey. Now, I have snookered students who fell into my pit of despair here, and they eventually got the right answer. But they believed, they did use the fundamental theorem of line integrals, that's fine, but they first used it on, going from the beginning point to the layover stop, and then they added that to the second part of the journey where they started it, where they left off, and they finished. And that will give you the right answer. But because you wasted so much valuable time, I don't give you full credit. Like, you should have known that you don't need to do that. That's wasting valuable time. Well, why? Because look, you only need to care about the beginning and ending spots. You don't care about the layovers when it's conservative. Now, folks, if this vector field weren't conservative, oh yes, you would have to care about any intermediate stop. But here, we're just going to go find the potential function, and we'll care about the beginning point and then the final ending point right here. No intermediate stops needed. Now, first, to prove it's exact, we are going to show that it is conservative. So how do we do that? Well, anything multiplying with the dx, that's understood to be the m component of your vector field, and then the dy factor there, x squared z, is n, and then x squared y is p. Okay, so let's get dn dx. And the partial of x squared z with respect to x, I believe, is 2xz. Is that the same as dm dy? What do you think? The derivative of 2xyz with respect to y. Is it 2xz?
Yes.
Yeah, it is. So this is check. This is good. We got it happening. Now let's check if dp dx is the same as dm dz. So when I take the derivative of x squared y, that's my p, with respect to x, I get 2xy. Is that the same as dm dz? Check it.
Yes.
So, yep, you got that happening. And then finally, you need to check if dp dy is the same as dn dz. So when you differentiate x squared y with respect to y, I get x squared. Is that the same as dn dz? And it is. So we have all three happening. So therefore, the vector field is conservative. And the differential form is exact. You've shown it all. So now what? Well, you still have some work to do. What do you need to do? Go get mama. Go get that potential function, just like we did in the previous problem. Integrate, 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 and then add the results. Okay, so of course I'm running out of room. What else is new? When? myself more room here. All right, first let's integrate m with respect to x. So what is the integral of 2x, y, z, dx? I think that's going to be x squared y z, and then acknowledge there's extra junk. H of the other two variables, y, z. How about n dy? So the integral of x squared z dy. Well, that's just going to be x squared yz plus g of x and z. And then finally p dz. Okay, p was x squared y, and integrate that with respect to z. Oh my God, I got all of these are just duplicating. Everything is a duplicate. Do not add all these together. Now, a student about a semester or two ago said, well, is it ever possible where you get, say, you know, some expression, let's say x squared y z, but in another one of those integrals you get the opposite? So do they ever subtract out? That will never occur. Good question, but it won't happen. And if it does, you did something wrong. Okay, be careful. So your potential function, and I'd like you to label it, actually write down physically fxyz, is x squared yz plus some constant. And now what? Well, now you can do this line integral. This line integral FDR, which is the same as, you know, the mdx plus the n dy plus the p dz. Remember, I told you these two forms are really the same. The differential form is just where somebody did the dot product for you. This is just going to be the potential function evaluated between the beginning point, 1, negative 1, 2, and the final destination, 1, 4, 3. Okay, so substitute in the final destination first, minus, and then substitute in the beginning point. And let's see what we get here. 12 minus a minus 2. Woo, okay, I get 14. And there you have it. The line integral is 14. So to recap, this is the type of problem that's in differential form, and they want you to show it's exact. And that's just a fancy schmancy way of saying show the vector field's conservative. And if you've taken differential equations, you know what an exact DE is, an exact differential equation. It's where dm dy equals dm dx. Vector field's conservative. So that's where the two connect. Pretty good, huh? So we showed it was conservative, and then we recovered the potential function and applied the fundamental theorem of line integrals. And boom, we get our answer. Okay, I'll pause. Any questions so far? Okay. So this next problem is similar to what you're going to see in homeworks. And they try to trick you into doing something. And if you get tricked, that's too bad for you. Like if you get tricked into doing a lot of work, even if you finally get the right answer, I'm going to take away points for wasting time. So what kind of quick connection can you see here? And I'll go slow. We'll read it. That is just sort of obvious and makes this problem doable within like 20 seconds instead of 5 minutes for people who don't see it and end up doing a bunch of work that they didn't need to do. So they're giving you a potential function here. Okay, that's a scalar function. This is not a vector field. Please don't tell me this is a vector field. It's not. You know, a vector field is the kind of function that has component form, and it's got, you know, the angular brackets, or it has the standard unit vectors linear combo version. So this is just a scalar function. So you know it can't be a vector field. So here they're asking you to do a line integral. Now normally when you see one of these line integrals, I can't spell today, you see F dotted with DR, you know, does not stand for Franklin Delano Roosevelt, FDR. That's the usual look. I've called these type 2 in my lecture notes, okay? Vector line integrals, vector field line integrals. So this sort of has that look, but not quite. So what the heck? What do you think? Isn't this supposed to be F?
No.
Or is it?
The same?
They're the same. Thank you. Nathaniel sees it. Congratulations. So what are they saying? They're saying that this is a vector field. Remember, gradient is a vector field.
Oh yeah, I do.
Hello, are you guys awake? If you don't
Yes.
get this, you're gonna blow it. The great students are able to make these connections in their mind. A gradient is a vector field. And folks, what have we been doing here? Finding a mama, or the potential function for these vector fields, because they're conservative. Please go back to the definition of conservative vector field. A conservative vector field is essentially a vector field who is somebody's gradient. That's the whole thing. That is the whole point. Maybe I should just write that down, because I could make that a true false question. Would you be able to get it? You know me, I love true false. You think that's going to be on a future exam? Oh, I love true falses. They're always going to be around. Man, I love those babies. Yeah, cool beans. So please note that a conservative, this is a fact, okay? A conservative vector field is a gradient. And sometimes they call that a gradient field. It is, because gradients are the ones that are conservative. So obviously, if you're somebody's gradient, your del little f, you have a potential function. And that is the little f. That's your mom. It's like, hi, mom. You're my mom. You're my potential function. So what are they doing here in this? Take the line integral of del f dot dr. They gave you the vector field. That's it. It's the gradient field. And so do we have to go get the gradient for this function? You know, fx, fy, fc. Should we go get it?
Oh,
No.
No. Why
Yeah.
would you do that? Not necessary. Not necessary. No need to go get. Why not? You're getting really confusing. I don't get what's going on. Pay attention. Because you will. I love this trick problem. And I've had students do it and get the right answer, but waste time. And I just took points away because they wasted time. Look, they're giving you the mama function. They're giving you the potential function. This is the potential function. Here it is. They're handing it to you on a silver platter. You can't ask for anything better. And then they're going, hey, evaluate this line integral from this point to this point. You don't have to do a lick of work except for the fundamental theorem of line integrals. So you don't have to go get del f. You don't have to go do that. You're already guaranteed that since del f is a gradient, it's a conservative vector field, and they gave you the mama already. Yahoozers. So this line integral dr is equal to your scalar potential function evaluated between the starting point and the stopping point. Don't need to do any work except for substituting in stuff. You know, don't bother, finding the gradient, or you don't have to do any integration and none of that stuff. You're like ready to rock. So, don't go off into the weeds. You want to think, be a thinking student. The thinking student really understands what they're learning, not just, oh yeah, I've seen one of those problems. I know the technique on how to do it. I don't know what the heck I'm doing, but no. The students that do well on my final are the students that really are understanding these concepts. They know it, not just, oh yeah, I'm going to do the procedure, blah, 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 whatever. I don't know why I'm doing it, but that's how she did it in class. And that's what the course reader says. No. So we're going to evaluate xyz plus z squared between these 2 points. Okay, fine. So what are we going to do? Well, start plugging stuff in. So let's see, we've got 4 times 6 times 3 plus c squared, that's 3 squared. So I just plugged in the ending point minus, and then I'm going to plug in the starting point 1, 0, negative 2. So 1 times 0 times negative 2, but that's just 0 plus z squared. Okay. And then what the heck? This is what? 24 times 3, 72 plus 9 minus 0 plus 4. I get 81 minus 4, which is 77. Boom, I'm done. And that luckily is one of the choices on the multiple choice. Woo, thank God. Thank God it's there. It must have disappeared. I don't know what the heck just happened to it. So that's letter G. That is the correct answer. Okay, so any questions on this? They're pretty much giving you a lot of stuff already. Okay, so now this next example, I love this next example because what I did is I took a colleague's problem that they had put on a differential equations final that they were sharing with me, and I was so impressed with it. I modified it and used it to put in my calculus 3. Whoa, we're not doing differential equations. No, you don't have to, but there's that connection when the differential equation people start doing exact. So you remember how I get really strict about, and I told you this, I get really strict about you doing, adding a little bit extra here. When you recover the potential function, whether this is the 3D version, but I even mentioned this last week when we were recovering potential functions for two-dimensional vector fields. You got to add those guys. And I said, if you don't add these, I'm going to take points away. Don't just put plus C or plus some other Yahoo stuff because you don't care. I care. I care very much. And here's why. Check out this problem. You would have gotten it wrong. This was a challenge exam for differential equations. Loved it. So here, they're not even asking you to evaluate the line integral. They're just saying, hey, if possible, find the n function, that's this guy here, multiplying with the dy, that would make this line integral exact. You don't even have to evaluate the line integral. They didn't give you enough information anyways. So how would you figure out how to get the n? Now here they gave you the m, but what the heck? How are you going to get the n? So watch closely because I claim you know how to do it, or you've got the tools to help you go do it. Yeah, anytime I use my erase tool, my Microsoft Surface Pro goes nuts. Thinks I want to erase the whole world. It's like, hey, I don't want to erase the whole world. I just want to erase something that I just did earlier, not everything on this page. Okay, so you've got your m, and then who knows what n is. So the goal is n is equal to who knows what. Okay, and we're going to get the format for it. So let's go recover the potential function, because if it is exact, there is a potential function. There has to be. So that's the whole point. So you're like, okay, so snip and sketch. Oh man, please don't take snipping tool away from me. That's the only way I function. I don't know if you guys like snipping tool, but I do. Okay, so what I'm going to do is I'm going to integrate m with respect to x. And this is going to take a little bit of time because this is kind of a hard problem. And so I do like this teacher's style. They make things a little bit tricky. Love it. So we're going to integrate with respect to x. Now this first term is not that hard to integrate with respect to x. You keep y constant, so I'm just going to copy down the y to the half. And when you integrate x to the negative a half using the power rule, you'll get 2x to the positive a half. Fine. Plus, but then how do we integrate this second term with respect to x? Well, I claim we can use the log rule. Integral of 1 over u du is ln absolute value of u, where u is x squared plus y squared, and du, the derivative with respect to x, is 2x dx. Now, good news and bad news. Good news, I already have an x dx in the integrand. Yay. What's the bad news? Well, I'm not seeing a 2 there, so I need this. So I'll put 1 in, provided I divide 1 out. And now this integral looks like 1/2 1 over u du, and so we'll get 1/2 ln u, but that's 1/2 ln, and I don't need the absolute value because x squared plus y squared is guaranteed to be something positive. So what do I have right now? I have that so far, and I'm not done. So let's clean up this problem here. I've got this plus this plus extra junk, and that's the key here, g of y. So what do we have so far? We have f xy is equal to what we have so far, this term, 2x to the half, y to the half, plus 1/2 ln x squared plus y squared plus g of y. Okay, that's what we have for the potential function. And how do I get the g of y? Well, I'm not gonna. Here's what's true that you have to know, is that the n here, if this is definitely an exact form, this is supposed to be mama's first partial with respect to y, by definition. So what are we saying? N is the first partial of the potential function with respect to y. That's what we're saying here. If you get that connection, congratulations. So I don't really have the full potential function the way I'd like it, but so what? Let's go ahead and get the partial derivative of f with respect to y, and that will be the format for n. Okay? So when you take the derivative of 2x to the half, y to the half, with respect to y, you get 2x to the half, and then using the power rule, I'll have a half, y to the negative a half, like that. Ooh, okay. Plus, and then I'm going to take the derivative of this logarithm with respect to, was that x squared plus y? Ah, sorry. Let me just check here. Yeah, that was supposed to, my bad. This whole, I copied it down wrong. None of you said anything. X squared plus y was the denominator of that. Doesn't change much here. Although we are going to need absolute value. Ooh, yeah. X squared plus y. Okay, that was not squared. All right, now we're going to take the derivative of 1/2 ln x squared plus y with respect to y. So we have a half times 1 over x squared plus y times the derivative of x squared plus y with respect to y. I think that's just going to be a 1. Plus g prime of y, and I'm done. So what's the correct answer? This right here. This is your n. Well, what's g prime of y? You don't need to know, but you do need to put that in there as part of your answer, because n has some other junk in there. So that's the point. And this is a pretty abstract problem, but that's what I love about it. It's really acknowledging this extra stuff that I put in there. Okay, so now let's look at equivalent conditions. There's a meme for you. Life, man. It's a line integral in a conservative vector field, bro. That's right. You didn't even know it. Okay, let's talk about what if your curve ends up having the same starting and stopping point. I mean, it could happen. So if a line integral is independent of path, then if you're using the line integral to compute work, which is a very, very relevant application for line integrals, let's say you were asked to compute the work done from this point to the 2, 1, but then, so you went from here to here, but then let's say you went from 2, 1 back to 0, 0. So then you go back to where you started from. So then the beginning and ending point are the same. So what do you think the work done would be?
0.
Yeah, work done will be 0. Very good. Fantastic. Quick definition, a curve that's R of t represented, and you have A and B as your time interval, is closed is a closed curve if when you evaluate R at the first time slot, a seconds, it'll be exactly the same point as the vector value function evaluated at the ending point, because it basically, it meets. So, you know, here, let's say you go over here to this point, but then you come right back to where you started. That's a closed curve. So now let's do equivalent conditions. So this theorem, I claim you already know 2 out of the 3. So if even one of these things I'm about to list here is true, you get the other 2 automatically for free. The other 2 are true automatically for free. So that's equivalent conditions here. So first you have a vector field, Mn and P. And by the way, this theorem is just as good for 2-dimensional vector fields as it is for 3. So don't think it's only pertinent for 3. It works for any vector field. Okay, you've got a piecewise smooth curve. The following 3 conditions are equivalent. Remember, if one is true, the other 2 you get automatically for free. So number 1, if F is conservative. What does that mean? Remember, that means that the vector field is the gradient of some potential function for some potential function F. Okay, what is true also automatically for free? This line integral f dot dr is independent of path. Oh, but we already knew that one from a previous theorem. I know, but we're going to add one extra thing on here that's also true for free. The line integral f dot dr is equal to 0 for every, and I mean every, closed curve C in the region R. You get that for free if it's a closed curve. So those 3 are all equivalent to each other. If one is true, the other 2 are true automatically. Now you have to be careful because I've seen students screw this up, and this could be a very subtle true-false question. Suppose you did do a line integral, just say, and the curve happened to be closed, just say, and you got a 0 for that one special case. And could you go, oh, I get those other 2 for free because it says so? You have to be careful because it might have just been a fluke, like that particular special weird curve that happened to be closed. Your line integral was 0, but it's not true for every closed curve C and R. So you have to be careful because that line integral would have to be 0 for any and every closed curve. So if you just found one that it got 0 and then the other ones aren't, then you don't get the other 2 for free. Sorry. So it's a little bit tricky. Now let's look at some notation for closed curves, line integrals. If you know your curve is closed, you may see a little circle right there on top of the integral symbol. That will mean the curve is closed. Kind of cute. So let's do a couple of examples and then we'll be finished with this section. Okay. So here's a line integral, and they're asking us to evaluate it on this path and then another path. So let's actually sketch the paths and take a look at them. This path starts at 0, 0, goes to the point 4, 1. So that's the first leg of the journey, C1. And then to 2, 3, up here. So the second leg of the journey is right there. We'll call it C2. And then back to where we started, C3. So I hope you can tell this is indeed a closed curve. Okay. Why? Because it starts and stops at the same place. So then what? Well, let's see if this vector field is conservative. So I'm going to do this wrong, and then somebody point out what I'm doing wrong. Let's see if you can see it. I'm going to do what a common student error is. So I'm going to do it the wrong way first. So I'm going to ask this question, what's wrong with what I'm doing? Okay, so first, I am going to check to see if the MDY is equal to dn dx. That's what I'm about to do right now. And that's good because if it's true, then the vector field is conservative, and then the line integral is going to be equal to 0 because this is a closed curve. So let's see, here's m and n. Okay, so dm dy looks like it's equal to -3, and dn dx looks like it's 3. So these are not equal, so not conservative. Does anybody see what I did wrong? This is a common student error.
Yeah, so it's a minus
Mhm.
3x plus 5, not minus 5 dy would be a negative.
Very good. Yeah, a lot of times, and I'm not the only one who's going to try to trick you. It's not just in my lecture notes. You'll see it in the homework. And if you take differential equations, they try to mess with your head there. Also, you're supposed to know that differential form, by definition, I defined it a couple pages back, is mdx plus ndy. And they put a minus there. So what do you need to do for yourself? You need to change that to plus a negative and then distribute the negative over any and all terms for your n. Okay, so you should have done that first before you did the dn dx. So I claim my real dn dx is not 3, it's what?
-3.
-3. So they are equal. Yay. And the vector field is conservative. So then what? Well, then you don't have any work to do. The line integral result is equal to what?
0.
0. I'm done. Closed curve, vector field conservative, boom, by the previous theorem. No work. I don't need to do a darn thing. I'm done. End of story. How about this second curve? They start at the point 0, 1. Okay. They go all the way down to the point 0, -1, and we'll assume it's a straight line. Okay. And then they go along this graph, which happens to be the right half semicircle of a circle centered at the origin of radius 1. Hey, this is a closed curve. They're trying to trick me. I'm not going to do any line integrals. My answer is 0.
Bro?
I do not feel like doing any work there. Don't need to. I'm doing the same vector field, and it's also a closed curve. So why should I do any work? Don't need to by the previous theorem. Okay, so I'm done. Now, I love this meme because it's funny, and you may not think it's that funny, but please don't get caught thinking that, you know, anytime you have a line integral, you have to go parameterize. Because if it's a conservative vector field, you don't have to parameterize anything. Go get the potential function instead, because otherwise you're doing a lot of hard work, and then you're killing an adorable math puppy by doing a bunch of unnecessary work. Yeah, you don't want to do that. You don't want to be guilty of puppy murder. That'd be a bad thing. Okay. So this is a good time to sort of take a quick recap on what happened before I'm going to get into greens right now. And I was, yesterday, I was just sort of looking at some folks' quiz results. And I think, and this happened last semester and the semester before. So let's clean up some stuff. There's 3 types of line integrals. And I did have a student ask me this in office hour, how do you tell the difference between any of the 3? Like, how do you know which one is which or whatever? Do they have to tell you? Or should you just know, or what? And the answer is you need to just know. Okay, so the 3 types and the way they look. Okay, the scalar type, it has this look to it. It's going to have a scalar function, and then it's going to have ds. This is the arc length element. It does not mean dx. Please note this is not dx or dy, not dx. And the arc length element, that ds is a pain in the patooski to go get, because you're going to have, you know, you need some vector field r of t, and then the ds is the magnitude of the r prime dt. This is the arc length element, and you have to go get it every time. And if you neglect to go get that, ooh boy, your scalar line integral is not even going to be close to being right. Okay, so that's how I know I'm dealing with the scalar line integral. I see the line integral and I'll see that little ds. Boom, scalar line integral. That's my red flag. What about type 2? Now, type 2 and type 3 are both vector line integrals, but they do have a little bit of a different look. So, and they both can represent work. Both can represent work done. I can't spell today. Work done on an object as it moves through some vector field. Now, these two types, you need a vector field to go do them. So if they don't give you one, then it's given to you maybe a differential form. It's given to you sort of, that's an integral part of it. It's kind of disguised, but you need to do it. Scalar, no vector field involved in a scalar line integral. Well, then what's it good for? Well, it's good for mass of a wire, basically. That's what I use it for. That's pretty much, I think, the only really good application for it. Okay, so the second type, what does it look like? So type 2 is going to look like this, f dot dr. So you have to go get the vector valued function, take its derivative, and then you have to do an actual dot product here, a dot product between your force field and your tangent vector to your curve. You don't do the dot product, you're screwed. Does it need an arc length element? No. You don't have to go get the magnitude of the velocity vector. You don't have to do that, because remember when I derived this for you, that canceled. You just have to do a dot product. Now, what about the type 3? Type 3 is differential form. This is differential form. So a 2D differential form, mdx plus ndy, the 3D mdx plus ndy plus pdz. Okay, and if the differential form is exact, that means it's a conservative vector field. The differential form isn't you may get differential form that's not exact all the time, and you have a lot of work to do. The difference between 3 and 2 is that this type, somebody did the dot product for you already. So the dot product was done for you, so you don't have to. You have to do a lot of substitutions and stuff if the vector field isn't conservative. So that's the 3 types of line integrals. And then conservative vector fields are great because for 2 and 3, if the vector field is conservative, you don't have to do the line integral by brute force where you have to parameterize and do all that hard work. You can just use the fundamental theorem of line integrals. Okay? If it's not conservative, then you have work to do. So that's kind of a nice recap. Any questions on this? Okay. I have no idea what that is. Interesting. Well, let's take a look. May have redone it. Yes, indeedy. Whoa, Windows, love it. Okay. So we're going to look at Green's theorem. So let me remind you that we're in the middle of doing the vector calculus portion of this whole class. So if I go over all these modules, the first thing that we did in this class is we did vectors. And we just looked at, the first couple weeks, what's a vector? How do you, take a dot product of a vector, magnitude, all that stuff. So we did all that. What's the second module? This is good review for the final, so pay attention. Vector valued functions. So what? Well, here we did R of t, and then we did a lot of stuff with vector valued functions. We used it to represent motion, like projectile motion, for example, and learned what a velocity vector is. And we also looked at t and n, you know, what are t and n, the unit tangent vector and the unit normal vector. And we also discussed curvature. And so all that stuff's going to be on the final. Don't worry, it's going to be on there. Then what? The next module, the next two modules are the multivariable calculus portion of the class, the multivariable calculus. So the first module was partial derivatives and all the things that you're supposed to know with partial derivatives. Yeah? You know, is intro to vector, this was included in an intro to functions of more than one variable. Because you need that when you're going to do multivariable calculus. Hello? That's what the multivariable means. Multi means many, variable, you know, variables, multivariables. So we got an introduction. We did level curves. We did partial derivatives. We found limits. I mean, you found limits here in vector valued functions also, as well as integration and differentiation. And here you learned how to take partial derivatives, and you learned about the chain rule, directional derivatives, gradients, tangent planes, normal lines to surfaces, all sorts of stuff. And then we even did advanced stuff with partial derivatives, like finding extrema, including Lagrange method of Lagrange multiplier method, all that. That was this right here. The third module was multiple integration. So you're still doing multivariable calculus, but here's where you do double and triple integrals and all the relevant stuff to how do you evaluate and set up double and triple integrals. Okay, that was exam 3. And then finally here, we're in vector calculus. So we've already done the first 3 sections of vector calculus. What did it involve? Getting introduced to a brand new function called vector fields. Then what? Talking about conservative vector fields. And then what? Line integrals. Yeah. And then fundamental theorem of line integrals and independence of path and closed curves and those things. And now we're going to do even more. So we're going to continue our trek. So what does that involve? Green's theorem, baby. Yeah. So what? Yeah, it's good. It's awesome. This is one of the most fun parts of the whole class. You're going to love it. Really? Yeah. Exciting stuff. I'm excited for you. You get to learn something really cool. So we're going to use Green's to evaluate a line integral. Oh man, you mean line integrals aren't going away? They kind of are. You'll see. If you can apply Green's, no line integral necessary. And then using alternate forms of Green's. All right, fine. First, let's do a quick definition. Actually, a couple definitions, then we'll hit you with Green's. So what's a simply connected region? We did a connected region last week. We did a connected region that if you have any 2 points in a region, it can be connected by a piecewise smooth curve. And we talked about like how Hawaii is not connected. You've got different islands. But what's simply connected? Simply connected, and here's some diagrams here. This right here is simply connected. These guys are not. So how do mathematicians technically do the definition? Because pictures don't qualify as a definition in math. So how do you say what you see here using words? Aha, it's not so easy. So we're going to do a couple definitions. First, simple curve. A simple curve, if you have a vector valued function, it's simple if it does not cross itself. And you'll notice in one of those not simply connected regions, this guy crosses himself. That's a curve that crosses over itself. So we don't want R of C to equal RV for any C and D in the open interval. Now you're ready for simply connected. A plane region R is simply connected if its boundary consists of one simple closed curve. That's it. That's the definition of simply connected. It wasn't that hard. So if you look at your diagrams, this here, there's only one curve that's the boundary of that simply connected region. This thing here, the one that's got holes, he's got 3 different curves that make his boundaries. The outside, and then you have to have two curves around those inner holes, because those holes are considered boundaries, if you will. And then this guy is because he doesn't, you know, have a nice curve that his curve crosses himself. It's not simple. Okay, now you're ready for greens. Here you go. You got a simply connected region. Nice. You've got your boundary, which is a nice curve, and it's oriented counterclockwise. Please note. Counterclockwise. What about clockwise? Just the definition, the way greens was developed, counterclockwise only. We can still do clockwise, but we'll get the opposite result, okay? We want the curve to be traversed so that when you drive around the island, you can look over your left shoulder and see your island. So if you look here on this island, if you will, if I were driving around the border, I'd always be able to look over my left shoulder and see the island over my left shoulder. And you may think this is really like superfluous information, but trust me, next time you'll see it's not. It's key. So if you got that happening and M and N are continuous partials, then if you're doing one of these line integrals, and it could be differential, by the way, it does have to be a closed curve, closed curve, closed curves only for greens. Put that down because I don't want you to using greens on curves that aren't closed. I want to put or f dot dr. You're not restricted to differential form, either type 2 or type 3. You can use greens as long as it's closed. So I'll put little circles here around the thing. That means they're closed. Then what? If you don't want to, and you'd rather do a double integral instead, you can. And the double integral that you'll do is this one. It's got the integrand dn dx minus dm dy. And this is so key, folks. Like you're going to have this on your last midterm and the final, and it's awesome. It's awesome. So what does it say in plain English? It says your double integral, this value of this double integral is basically the same. It's the same as the value of a line integral over the closed boundary. That's kind of cool. You get it for free. So I'm going to do a quick proof, and then I'll do one problem, and then we'll be done for today. And then we'll pick this up next time and do lots more greens. And I have some problems for you picked out you can try for greens. Okay, not too bad. So greens. So the partial proof, and I'm only going to prove half of it, and this is pretty standard. Let's say you had some really weird region like this. We'll call this point A right here, point A. Let's say this is some weird point B. This will be C1, and let's say C1 is given by y equals f1 of x. And it's got to be a closed curve, so we got to go back to where we started. So let's say the curve goes the second leg of the journey. So this is a nice region here. And let's say this curve is given by y equals f2 of x. Fine. So here's what I'm going to do. This is a partial proof. I'm going to prove that the line integral m dx is going to be equal to the opposite of dm dy dA. This is what I'm going to show. I will show this. Well, why does that matter? Well, if you look at greens, sort of half of it, you're going m dx here, and then you've got this minus m dy. Okay. So let's just look at the line integral, just this curve, closed curve. If we were going to do it by brute force, you'd have to do, two line integrals. One for C1. We do a color change here. So you do this line integral, which isn't closed. And then you would add that to the C2. Like this. Okay. Well, interesting. So then what? Well, if you were doing this, you would go from A to B, and you would have M. M is a function of x and y, so you'd go x, but y on C1 is f1 of x, like that, dx. Plus, now this second line integral, you're kind of going backwards because you're starting here at the B, so I'm going to have that B, and then you end up at A over here, and your M is a function of X and Y. So the Y on this curve is F2 of X. Okay, fine. Then what? Well, you learned something from Calc 1 that said if you want to swap these limits, you can, so long as you take the opposite in sign of the value of the integral. So that's legal. And the first integral just stays the same, so I'm just going to copy it down. Then what? Well, one thing that you also learn in Calc 1 is if you're integrating with respect to the same variable, which we are, and the limits for two integrals are the same, and you're just subtracting two integrals, you can combine them into one big old integral. And we're going to do that. And take the difference of the integrands. Fine. Like that. That's one big mess. I know. So I'm going to save this for later. So OTH stands for on the other hand. On the other hand, if you consider this double integral R, the partial of M with respect to Y, dA, if I were to iterate this integral for this region here, this I shaded it in, there's R, using the vertical simple choice for a region of integration, X is going from A to B, Y is going from a low of F1 of X to a high of F2 of X, and then we've got my dm dy, and then I've got dy dx here, like so. If you do the innermost integral first, when you take the integral with respect to y of a derivative with respect to y, you guys know, because integration and differentiation are inverse operations of each other, you're just going to get the m, and you'll evaluate it going between the limits. And don't forget to plug in your upper limit first. So this is going to look like mx f2 of x minus, and then we'll plug in the lower limit for y. And then we'll have to integrate this with respect to x. But wait a minute, stop for a second. Stop. Compare that to what I saved for later. Are these almost the same? What do you notice is similar and what is different? Look at that. And then look at this. There's a slight difference, but not much. What is it? Does anybody see it? Subtle.
The first one from the second one, and it's like backwards.
Yeah, exactly. These are backwards. Exactly. Yeah, so they're the same, but one's opposite of the other. So therefore, we can conclude that the line integral, m dx, is equal to the opposite of the double integral dm dy. So I'm done with the proof. End of story. Okay. And you can do the ends in a similar way, but the ends that actually don't have a negative, they end up equaling each other. So then you can add it all together and get your Green's result. Okay, so there's your proof. And instead of doing a verify, what I'm going to do is let's go do example B over here first. And then I'll do A next time. I'll do B and then I'll cut you loose. Okay, I know everybody's kind of tired. I know, I'm tired. So let's say you're given a region R, and it's bounded by y equals 2x. So hopefully you know how to graph y equals 2x. What the heck? It's a line, and it goes through this point 2, 4. And then y equals x squared, all right. Like that, there's y equals x squared, parabola. And this is the region of integration. There's your region R. Well, that's a closed region. And the two curves, if I did have to evaluate this line integral, I would have had to do two line integrals. I have to go around this boundary counterclockwise. And yes, it would matter. You would first go along the C1 would be your y equals x squared, and you'd parameterize it and do all the necessary Yahoo stuff. And then for your second leg of the journey, you'd start here at 2, 4 and end up at the point 0, 0 along the graph of y equals 2x. So you get a second line integral and you'd add the results. And it would kind of be a pain in the butt. So I don't feel like doing this line integral. I claim that Green's tells me, hey, that's the same as a double integral over the region R. So long as I do, what Green says. What do I have to integrate? Just anything? No, not anything. Like, you better know what you're doing here. Go look it up. Oh, it's got to be dn dx minus dm dy. Mm-hmm. Mm-hmm. So not just anything. dn dx minus dm dy. Okay, well, who's m and who's n? They didn't give it to me. Yeah, they did. It's disguised, but you know differential form. So the m is the stuff that's multiplying with your dx, and your n is understood to be multiplying with your dy. Okay, so then I could go get dn dx, because the derivative of x cubed with respect to x is 3x squared. Bingo. Minus dm dy. So the partial of 5xy with respect to y is 5x. And now let's iterate the integral. I'm going to choose my favorite order of integration, dy dx. Did you think that integration was going to go away? I know some of you had a lot of trouble with exam 3. It's coming back. Like if you haven't ironed out the kinks with setting up and iterating double integrals and all that stuff and figuring out your boundaries and all that good stuff, it's here again. Hopefully now, and I encourage you to get clear on all of it now, because it's going to be here happening in Greens, like a lot. So if I put my little man in my region here, whoop, there's the little man here, standing straight up. If I iterate what's going on with the x, because that's always got to be pure numbers for your outermost integral, it looks like x is going from a low of 0 to a high of 2 on that little region. Fine. What's y doing? Well, y certainly isn't going from 0 to 4. And that's dangerous for you to even say that. A lot of folks did stuff like that on the exam a week or two ago, and it was like, oh my goodness, you know, what was it, last week? The only time everybody is pure numbers when you're doing rectangular coordinates is if your region looks like a rectangle. Does this region here look like a rectangle? Not really. So only the outermost limits are going to be pure constants. So the man's head is on the upper limit. That would be y equals 2x. His feet are firmly planted on the parabola, which has the equation y equals x squared. Boom. I'll give you partial credit if you at least set up the double integral correctly. That's worth some weight in gold right there. Partial credit points for sure. Now what? Go integrate. This is just double integration stuff. So 3x squared minus 5x, you're going to integrate it with respect to y. Well, that just looks like a constant with respect to y. Exactly. So I'm just going to leave it and then put the y there and evaluate the y going from the lower limit of x squared to the upper limit of 2x. And you know the drill. You're going to first plug in the upper limit because you're supposed to by the fundamental theorem, and then plug in your lower limit. And then this is just a Calc 1 problem. Yeah. Go ahead and FOIL this mess out because you need to before you integrate with respect to x. So 3x squared times 2x is 6x cubed. 3x squared times negative x squared is negative 3x to the 4th. Negative 5x times 2x is negative 10x squared. And negative 5x times negative x squared is plus 5x cubed. Okay, now I can integrate this mess. All right, well, let's see. I'll just go ahead and do it. What do I got here? What I like to do before I integrate, though, is I like to combine my like terms because I can, because those are x cubed terms. So let's combine them into one term there. So I'm going to have 11x cubed, and then I'll have the minus 10x squared minus 3x to the 4th dx. Okay, I got my descending, well, not really descending powers, but okay. So then my antiderivative 11 fourths x to the 4th minus 10 thirds x to the 3rd minus 3/5 x to the 5th. And I'm going to go for from 0 to 2. And then, you know, arithmetic, not my strong suit. Yeah. And I get, plug it all in, I get negative 28/15. That's the exact answer. And that's approximately negative 1.861. Now, when we did double integrals for that last unit, our double integrals primarily would end up to be positive results. Why? Well, because those double integrals represented volumes of solids, or they represented areas of regions, or they represented mass. Okay? So it wasn't okay to get like a negative number. But here, this is totally okay to get a negative number when we were doing this double integral. Why? Well, because this isn't representing volume of a solid at all. It's representing a circulation around the boundary of this region. Yeah, and we'll talk a little bit more about that next time. And remember, line integrals represent work done too. So it's representing also work done. And work can be positive, negative, or zero, as any physics person will tell you. So negative answers, legit. I'm okay with it, as long as I didn't screw up anything else. Okay, so questions?
Did we fill in why that the vector field conservative part?
Well, there's no need for the vector field to be conservative when you're using greens. In fact, Nathaniel, I'm glad you asked that question because it's an excellent one. What would happen if you were applying greens, Nathaniel, and dn dx was exactly equal to dm dy? Do you get you would have conservative? Yeah?
Yeah. So it would end up
This
being
would be zero, right? And your answer would be zero. And why is that? Because you're on a closed curve. Remember that to use greens, you have to use a Green's theorem on closed curves only. And the equivalent conditions theorem we did about an hour ago says, if you've got a conservative vector field and you're evaluating a line integral on a closed curve, the answer is
zero.
yeah. So yeah, using greens, you don't have to show it's conservative or anything. In fact, if it is conservative, you're going to get zero for an answer. So you won't even, you'll be wasting valuable time going through all this integration and setting up the double integral and everything. No need.
Okay.
Yeah. Uh-huh.
Thanks.
Any other questions on this? We'll pick this up next time. We'll do more.